Scaled dimensionless intrinsic thermodynamic properties for a universe system. Scaled, dimensionless parameters such as the equation of state parameter, omega, the deceleration parameter, q, and density fraction, omega, are of special significance and utility in cosmology. Consequently, scaled dimensionless parameters of this type for the intensive thermodynamic properties of a universe system are defined in this study as where beta y denotes a scaled dimensionless parameter for a thermodynamic property and y denotes an intensive property such as energy density, pressure, temperature, and entropy density. The space fluid constant of the study is denoted by psi. Values for the energy density, pressure, entropy density, and temperature for the observable universe obtained in this study are recast in the figure given below in terms of scaled dimensionless values obtained using the beta y equation above. The beta y parameter captures the full natural range of these intrinsic properties while scaling them to a range of 0 to 1. This scaling is possible because these intrinsic properties have maximum and minimum values in nature which occur in space fluids. In addition, the ratios of maximum to minimum values for these properties, e.g., YPL/IVAC, have simple relations with the space fluid constant, psi, that was introduced in the second communication of this series. In the figure below, the beta y values for the Planck fluid intensive properties plot at 1, 1, circle symbol. The vacuum fluid values of beta y for energy density and pressure are at 0, 0, square symbol, while the vacuum fluid values of beta y for entropy density and temperature are at 0.5, 0, square symbol. Values for radiation fluids shown in the figure above were obtained using the equations from the photon gas theory of quantum mechanics. These equations allow calculation of temperature, pressure, and entropy density for a radiation fluid of known energy density and degrees of freedom. Using a value for the degrees of freedom, G** of 3.0396 in these photon gas equations ensures that radiation fluid reaches the Planck density at the Planck temperature. For comparison, G** equals 2 for a photon. The degrees of freedom in the very early universe is expected to be at least 2 orders of magnitude larger than that of photon radiation. However, calculations in the present study indicate that provision for more realistic G** values in early times would not qualitatively change the results shown in the figure below. Calculations of pressures and temperatures at energy densities where matter and vacuum contributions become important were carried out using the procedures of the Standard Model and the vacuum properties from this study. Figure 1. Scaled dimensionless values of ρe, ρs/kb, p and t for a universe system. Blue curve is pressure energy density, red curve is temperature energy density, and green curve is entropy density energy density. Discussion of the scaled, dimensionless values. The pressure energy density behavior shown by the blue curve corresponds to that of radiation from the Planck time until the early matter era, which begins at about 100,000 years after the CMB time. The green curve shows entropy density values. From this curve it can be seen that the entropy density of radiation dominates from the Planck time until about 1 millisecond. After this time, the constant vacuum entropy density determines the observable universe entropy density as the universe continues to expand. The time of 1 millisecond is when the entropy of the vacuum begins to dominate the entropy of the expanding universe. Before that time, the radiation fluid determines the entropy density. The scaled, dimensionless temperature values for a universe system and their corresponding scaled, dimensionless energy density values are represented by the red curve in the figure. Matter temperature does not influence the universe temperature because omega equals 0. Consequently, the universe temperature value drops from the radiation temperature values toward the vacuum temperature value as expansion occurs during the matter era.